Okay, so for this problem, we're asked to do 3 different traversals on this graph. So let's start with DFS preorder. DFS preorder is just listing the elements in the order that you first encounter them in a DFS traversal. So 61A is first. 61A has 2 neighbors, and by the tie-breaking scheme, we'll visit 61B first, so we'll write it down. And then at 61B, since this is DFS, we'll consider 61B's neighbors. Breaking ties, we'll visit 169 next. And then we'll visit 170, 188. And then we'll return from 61B back to 61A, and we'll consider 61A's next neighbor, which is 61C. At 61C, we'll see 169 has already been visited, so we return from 61C, and then we return from 61A. If we do the same traversal, the post order is just the order of elements from when we return from the nodes. So in our traversal, the first node we returned from was 169, then 170, then 188, then 61B, then 61C, then 61A. So overall, our DFS traversal looks like this. And 70 never gets visited. So for BFS, we first start at 61A, and then we'll visit all of its neighbors in alphanumeric order. So like this. So it's 61B, 61C, and then we'll visit the next level of nodes 2 away from 61A, which are these 3, and we'll visit those in alphanumeric order like that. And then we finished this problem. So in part B, we're asked to give a topological sort of the graph. Now there are multiple ways to topologically sort a graph. One way, which is a convenient way, is to just give the reversed DFS post order. So up here we have a DFS post order of all the nodes in the graph except for 70. So all we have to consider is where we would put 70 in the topological sort after having reversed these. So we know 70 has to come before 188 and 170, and nothing has to come before 70, so we can just put it at the front of our topological sort. And then we can just put the reverse DFS post order right after that. Alright, so in part C, we're constructing MSTs. The first part asks us to construct an MST using Prim's algorithm. So we know that 0 has been added to our MST so far. Now Prim's algorithm simply takes a look at all the edges connected to our MST so far and adds the smallest weighted edge. So with our MST so far, the next smallest edge connected to our MST is this one. So we'll choose this one. Minus 1000. The next smallest edge that doesn't create any cycles is the edge with weight 1. The next one is the edge with weight 2. The next one would be the edge with weight 3. Then the edge with weight 4 and 5. And after that, we see that we've connected all the nodes. There are 8 nodes, so we should have 7 edges in our MST. So just to double check, we have 1, 2, 3, 4, 5, 6, 7 edges. So we know we're done. Now let's move on to Kruskal's. So Kruskal's algorithm is slightly different. We instead look at all the edges in the graph and continually add the smallest edge to our MST as long as it doesn't create any cycles. So the smallest edge in this graph is the edge with weight negative 1000. So we'll add that to our MST. The next smallest edge is the edge with weight 0, then the edge with weight 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5. And we see now we have 7 edges. All the nodes are connected, and we finished our MST. Question 1D. Do the edges of the MST change in the graph from part C if we add 1000 to every edge weight? The answer is no. So in general, if you add a number to every edge in a graph, the MST won't change. The reason being that the MST is pretty much defined by the relative ordering of the edges by their weight. So if you take a look at Kruskal's algorithm, Kruskal's algorithm builds a correct MST by simply choosing the edges from least weight to greatest weight, as long as those edges don't create a cycle. So if we take all the edges in a graph and add 1000 to every edge, Kruskal's will still pick the edges in the same ordering for the MST, and so we'll still obtain the same MST after adding 1000 to every edge. Question 1E. For the graph below, let x be the unknown weight edge of DE. Can the marked edges in bold be a valid minimum spanning tree? If so, for what values of x? If not, why not? So let's take a look at this. If we inspect this, we can see that, yes, indeed, the edges can give you a valid MST. If we just let x equal, let's say, 1000, you can easily work out that these edges would be the edges picked by either Prim's or Kruskal's algorithm on this graph. Now, the problem is what ranges of x would give us a valid MST? We've seen that for very large values, it's a fine MST. But now we want to figure out what's the lowest bound for x. If we make x too small, then our MST algorithms might end up choosing ED instead of choosing the edges in this MST. So we want to make sure that x is big enough so that it doesn't change the existing MST. And the way we're going to do this is we're going to use the cut property. So if we take a look at vertex D and all the edges connecting D to the rest of the graph, we want to make sure this edge 0 is the smallest edge across this cut. So if x is greater than or equal to 0, then we know that this edge is indeed the smallest, one of the smallest across this cut, and so choosing this edge will still give us a valid MST. Now let's return to vertex E and consider that cut. We want to make sure that 1 and 2 are the respective minimums when considering the cut between E and C and the rest of the graph, and the cut between E and A and the rest of the graph. Now, if we make x greater than or equal to 2, this property holds. So we need both of these properties, so we just make sure that x is greater than or equal to 2. Problem 1F comes in two parts. The first part is to determine if the edges in bold are a valid SPT rooted in B. Now if you ran, let's say, Dijkstra's algorithm from B, we would in fact see that these bolded edges are the SPT. So we'll just leave that as an exercise. But you can confirm that these in fact are a valid SPT rooted in B. Now, we need to find a range for x that keeps this as a valid SPT. So we want to make sure that the edge weight for x doesn't change it at all. And the only way this edge x would change the validity of this SPT is if it provides a shorter path to E or through D through itself. We know that if we set x to an arbitrarily large value, it won't change the SPT because the algorithms will choose edges other than x because of its expensive cost. So we need to find the lower bound for x that keeps this tree valid. Let's first consider D. The shortest path currently, ignoring this edge x, from B to D is weight 0. The way to get to D through this edge x is through E, and the shortest path to E is of weight 3. So if x is greater than greater than or equal to minus 3, this edge is still going to be the shortest path to D. If it's equal to minus 3, we'll have two shortest paths, but this is still a valid shortest path. So we know that one condition is that x must be greater than or equal to 3. Now let's consider the path to E. The current path to E is of weight 3, and the only way to get to E through x is first from D, and the shortest path to D is of weight 0. So if we want that 0 plus x is greater than or equal to 3, which means we want x to be greater than or equal to 3. So as long as x is greater than or equal to 3, this path right here will still be a valid shortest path to E. So we have these two conditions, and the intersection of both of these conditions is simply x is greater than or equal to 3. So there we have our answer for the valid range of x.
So for 2a, we are given an array of symbols, and we are running insertion sort on this array, and we stop at a certain point in the middle of our insertion sort. Given this current state that we're at, we want to try to see if we can deduce some claims about these symbols. So how I'm going to approach this problem is trying to run insertion sort to try to see what things we can deduce first. So one thing we notice about these three symbols is that primarily we know for a fact that based on how insertion sort works, this hash has to go in front of the empt, the at symbol. So that means that we can deduce that this is true, right? Because the A stays where, in the first iteration, the at symbol stays, the hash moves down, and based on this insertion, this part of the array, we know for a fact that these two swapped. So after the second symbol, this is what the array is going to look like. All right. Then we move on to the $sign, and we can see that the $sign is in between the hash and the ampersand, and so the at symbol, and so the at symbol and the $sign need to swap. $sign at percent ampersand and then asterisk. So then now we can figure out, now we know this claim. Sweet. We continue on. Based on how this percent sign is positioned, we can see that it actually just stayed where it's at. So we know after the at is the percent sign. And then finally, this ampersand actually goes all the way down to the beginning. So it's just going to keep repeatedly swapping down until we end up with the state that is given to us. So then we can deduce these. We can deduce that the ampersand is in the very beginning, followed by the rest of these symbols. So this is what we know, basically. All right, so given what we know, let's try to solve this first claim. The ampersand is the smallest element of the array. So the problem is we weren't able to get to the point where we figured out the value of the asterisk. The asterisk could itself be the smallest element, but we haven't gone to that point in the insertion sort, so we can't know for sure. So the answer to the first one is that there's actually just not enough information to deduce this. Similarly, we actually don't know for a fact whether this asterisk is the largest element of the array. It could be the smallest, and we just haven't gone to that point of the iteration in which we swap it all the way down. So we can't deduce whether the asterisk is the largest element of the array. All right, what we do know is this one. We do know that the ampersand is less than the hash because it had to swap all the way down to get to its place. So we know this to be true. And finally, we know that based on the positioning of the @ sign and the % sign, that this must be false. The % sign is not less than the @ symbol. All right, so now for part B. For part B, we're basically looking at the Hoare partitioning scheme, and we're trying to walk through it pretty mechanically. So we want to see, after certain steps of the algorithm, what the array is going to look like. So we're given this initial array, and we are using 6 as our pivot. So basically what Hoare partitioning is going to do is that it's going to try to separate the array into a group of less than and a group of greater than. That's basically what Hoare partitioning is going to try to do, right? So how we're going to do this is we have 2 pointers, one in the front and one in the back. The one in the back pointer likes bigger items, and if it sees a smaller item, that's where it's going to stop because it doesn't like that item. The left pointer similarly is going to not like items that are greater than it, right? And so what happens is that basically these pointers move closer to each other until they both find an element they don't like. Once they both find an element they don't like, they simply just swap and continue moving down. So what's going to end up happening is that, let's do the left pointer first. The left pointer sees a 1 and it's less than 6, which is happy. So it's going to move to the 4. The 4 is still less than 6 and it's happy there, so it's going to move on. But now once it sees the 7, it doesn't like the 7 because the 7 is greater than 6. And for there, it'll temporarily stop. Now, if you look at the back pointer is okay with the 8 because it's greater, and so it will decrement down to the 5. Now here at the 5, remember that the back pointer likes bigger items than the pivot. And so it's dissatisfied with the 5 here. And so once we have both of these pointers dissatisfied, we do a swap. So after the swap is going to look like this, where the 5 and the 7 have swapped, and the pointers now move forward, right? And so then the answer for the array after the first swap is going to be this result. It's going to have the array with the 7 and the 5 swapped. Okay. So now, if we want to finish the partitioning scheme, basically the partitioning stops once the pointers have crossed with each other. And so what's going to end up happening is that this left pointer, again, it still sees a smaller item, so it's going to try to go to an item it's going to try to find an item that's greater. So these two are going to end up being in the same spot. And this is where you finish, because you've basically looked through all possible swaps in terms of greater and less than items. So the last thing you do is wherever the left pointer is, take the pivot and swap one more time. Because what that's going to do, so after effectively doing that swap, we get this result. And what that's effectively doing is creating a portion of equal to a pivot, creating the left portion that's less than the pivot, and creating the right portion that's greater than the pivot, right? So that's what that last swap is going to accomplish. And so this is what the array is going to look like after the partitioning. You just do one more swap by swapping the pivot into the middle. And that is the answer to 2B. All right, now on to 2C. Given an array, suppose that x, the value, is less than the y value, and that x appears to the right of y. What happens to the inversion count if we swap x and y? Filling completely all boxes that are possible. So first let's figure out what an inversion is. An inversion is basically any pair of elements that are out of order based on their relative values. So if we're assuming that we want all lesser items to the left and all greater elements to the right, if we have x less than y, but x to the right of y, that itself would be an inversion, right? And so we're trying to consider that if we swap x and y, what happens to the total inversion count of an array? And here's how I would like to think about it. So here we have the position of x, we have some elements here, we have the position of y, and we have everything here. And so and remember that inversions are with respect to just every possible pair, right? And so and x needs to be to the right of y, sorry. And so let's consider all the inversions from any element in the left side with respect to x. By swapping x down here, that will not affect any of the inversions because x is still to the right of anything in this left array. Symmetrically, if we swap y over here to where x is, that's not going to change any of the inversions to the right of y. So the only ones you need to consider are the ones in the middle, right? But when you actually do the swap, the number of inversions will basically remain unchanged with respect to all the elements in the middle, because if you're increasing an inversion, you're going to also decrease an inversion at the same time, based on the fact that you're swapping both x and y. So those inversions will not change, but you actually decrease an inversion by 1 by x and y itself, right? Because previously the pair y and x was an inversion. So by swapping x and y, you decrease the number of inversions. So finally, after the swapping of x and y, the inversion count can only decrease as a result. So for 2D, we are presented with a slightly different scenario in where we are trying to min-heapify an array using bottom-up heapification, and we're trying to figure out the inversion count as we do the min-heapification algorithm. And so the answer is going to be either it will decrease or it will remain the same. So for the it could decrease, the basic idea is going to be very similar to in 2C. Basically, the only way we can increase the number of inversions is if we take a large element and bring it closer to the front, or we take a smaller element and bring it closer to the back, right? But we're never doing that, because by min-heapifying an array, if we have this simple min-heap and we want to min-heapify it, then once we consider this 7 and try to sink down, this 7 is going to swap with the lesser item. And so doing this is going to move the larger item more towards the right and the small item more towards the left of the array, which is closer to their correct spots, which will decrease the number of inversions possible. The case where it stays the same is simply just if you have all duplicates. So if you considered a min-heap in which they're just all duplicates, then min-heapifying will just never cause any swaps because there is no need to swap, and so the number of inversions will just stay the same at 0. So for 2E, we have this interesting case of assuming we have this hash map that can map an integer array to its sorted version. How long would it take basically to do any accesses for this sort? So the answer is actually going to be no, that it is not possible in constant time. And the primary reason is that if you try to call .get on some x where x is some integer array, you have to calculate the hash code of it. In order to calculate the hash code, that requires doing some calculations on the array. And if the array is length n, the hash code is going to take theta of n. So it is not possible in constant time, and that's the reason. Because computing hash code takes theta of n time.
Question number 3. Back to the first half of the semester. Given two int lists defined as follows, fill in the append method so that it is non-destructive, important non-destructive, creates a new int list with y appended to the end of x. For example, if x is 3 to 4 to 5 and y is 9 to 10 to 11, then the result should be 3, 4, 5, 9, 10, 11. So for this problem, the key thing to note is that we want to be able to traverse through the entirety of X and then add on the end of Y, add on the int list Y to the end of that. So for our base case, we're going to want as normal, we want if X is equals to null. That means we have finished traversing to the end of X. We will worry about traversing through X in the actual recursive call. But for the base case, once we have reached the end of X, we're going to just return Y. Because if you want to append on Y to an empty list, you're just going to return the list. Now for the recursive call, we're going to return a new int list. Now returning a new int list is important because we want this to be non-destructive. Now the argument of this int list is because we just want to move over one element of X, we're going to simply copy over X dot first. And then we're going to recursively call append on the remaining elements. So that is X dot rest, comma, Y. And that's it. Question 3, part B. Suppose we modify our int list class so that it can be iterated over. Fill in the code below so that iteration works correctly. So we want to basically create an iterator class and then return that in our iterator method so that we can iterate over our int list. So we're going to, in our iterator function, simply create a new int list iterator. Which is a class that we will define below. And we're going to pass into this as the argument this, because this is the object that we want to iterate over. So within our iterator class, what do we want to do? So we basically want to be able to have a pointer to a specific int list object within our entire int list. And every single time we call the next function, we're going to move forward one element in our list. So I'm going to make a pointer variable of type int list. So this private variable will basically store where we're currently located inside of our int list. For the constructor, we're going to pass in an object of type int list. I will name that IL for int list. And so all we're going to do is start our pointer at the beginning of this int list. So we're going to set P equal to IL. And that's all we have to do. So in order to determine whether we have a next element or not, all we have to check is if P does not equal null. If P equals null, that means that we have reached the end of our int list, and so we should return false as a hasNext. As long as there's a next element, we should return true for our hasNext. Now for our actual next method, we need to basically increment our pointer one element forward. However, first we want to also return the value of the current element. So we're going to temporarily store, so I'm going to store in return val. We're going to temporarily store whatever value is currently located at our pointer. So I'm going to do rval and store it as whatever p.first is. I'm going to now move the pointer forward one, which is p equals p.rest. And then we're simply going to return rval. Question 3, part C. Suppose we have an int list from part B called L. There are 3 ways to iterate over L shown below. Assume that print is a method that simply calls system.out.print. So we want to consider this new case. Now suppose we change our int list iterator class in int list from public to private for each of our 4 files. What happens? Fill in one bubble per line. So we basically want to consider these 3 ways of iterating through our int list. And with this modification, will the code still run correctly? So to a reminder on what this code was, we had a public class int list iterator that we implemented, Originally it was public, and now we are changing that to private. So that is the only change in our code. So the first question is, does intlist.java still compile? So from this function, does our code still compile? And the answer is yes, it still compiles because none of the typing has changed. And because it's private, this class can still access the intlist iterator in all of its functions. So we have, the first one is compiles. In 1.java, we have an enhanced for loop iterating through our intlist. And so enhanced for loop do use the iterator function. However, our iterator function is still public in our intlist.java. So we can still return an iterator. And so this one is still also compiles and works correctly. For 2.java, we are now we are calling the iterator function in order to get the iterator, and then manually iterating through the function. So this is essentially the same thing as what happens in enhanced for loop. And so this one also compiles and works correctly because, as mentioned before, the iterator function still returns and is still public, and it just returns the object. And all the functions within that type are still public as well. So the hasNext and the next function. So now for the last one, we have 3.java. So now the difference here is we actually try to cast the iterator ourselves into a type intlist iterator. Now because this class is now private, no one except for the file of intlist.java knows about the existence of this class. So we actually cannot cast it ourselves, and so this part will fail to compile. Question 3, part D. Suppose we have a software system that makes a huge number of calls to a very large array list integer. We want to squeeze every last bit of performance out of the system. To accomplish this, an engineer suggests building and switching to our own special purpose int array list class. That is exactly the same as array list, except that it will use an int array to store the data. This is in contrast to the array list integer class, which uses an integer array. So in one class, we will use the primitives and store that into an array, and the other one we will store integer objects into an array. So we're now going to analyze the runtime of this new class and the space usage of this new class. So does the runtime get better, the same, or worse than if we had used normal array lists with integers? And so the answer here is actually it gets better. And the reason behind it is auto boxing and auto unboxing. So I will just write auto boxing /unboxing. So if you remember, auto boxing and auto unboxing is basically the conversion automatically from an int to an integer within Java. Now this operation, although in our normal code is not a big deal, when we're doing this over and over again, can lead to a pretty big difference in runtime. And so if we didn't have to do this over and over, it would make our overall runtime of our int array list better than our normal array list. Now how about space usage? So in the normal array list, we are storing integer objects. And in our new int array list, we are simply storing int primitives. And so int primitives are much smaller in size than a normal integer object, so our space usage also gets better. And the reason is because ints are smaller than integers. Question number 5, hash codes. Suppose we have the following class defined below. For each of the hash code implementations below, fill in whether the implementation is valid but slow, or invalid. So we're basically going to analyze all these different types of implementations. So the first one that we have is return UUID string. So if we look at the code above, we have a UUID string of type string with this value. So the answer to this one is that this hash code function is invalid. And the reason behind it is because remember that a hash code always has to be an integer in Java. And so because this is of type string, this is an invalid hash code. Our second implementation has return UUID string dot hash code. Now every single object in Java has to have a hash code, including the type string, which this UUID string is of type string. And so this will return a valid hash code. But this hash code will be slow because every single object of type sneaky snake will have the exact same hash code. And so you'll get every single object will collide inside of a hash table. The next one we have is return seed. So if we see from above, the seed is defined as an integer, private integer, that is passed in during the construction of the object. And so this is a valid hash code because it is a number, and it is in fact a valid and not slow. So it's just a valid hash code because every single object can have a different seed. So it is not inherently going to be slow. The next one we have is return random.nextInt. So the next int function of random simply returns you a random integer. So this one is going to be invalid because the hash code of an object should not change if the object does not change. But if you were to call random.nextInt 5 times in a row, you would probably get 5 different numbers. Or it is likely you would get 5 different numbers. The last one that we have is instantiating a random object. So we have a hash code ran equals new random with a seed of 10. And now we're going to return the next int of this random object. And so this one is actually going to be valid but slow. And the reason is because we pass in our own seed into the random object. And so every single time we perform this operation, when you call the next int function of the random object, given the same seed every single time, it'll actually just return the same number on every single call, as long as every single time you are reinstantiating the random object. But it'll always return the exact same number, and that will make it a slow hash code. So this turns out to be a valid but slow hash code. Question number 6, part A. For each of the following propositions about graphs, mark always true, sometimes true, or always false. So our first statement is A star finds a correct shortest path if it exists from a source vertex to the goal vertex. So we need to consider if we can come up with a counterexample, and if we can also consider an example where it works. And if we can come up with one of each, we will mark sometimes true. If we can only create a counterexample, we can put always false. But if we cannot create any counterexamples, we can put always true. So remember, from A star uses a heuristic, and we talked about the idea of admissibility and consistency in a heuristic. And what that means is an A star can work. So for example, if our heuristic basically doesn't exist, we are basically running Dijkstra's, which will always find the correct shortest path. However, if we gave it a very bad heuristic that is not admissible, it is possible that it does not correctly find the shortest path. And so the answer to this one will be sometimes true. Suppose we have a goal node in mind. BFS, breadth first search, finds a correct shortest path, if it exists, from a source vertex to that goal vertex in an unweighted graph. So the key part of this statement is unweighted. When we have unweighted, we can basically treat the graph as having every single edge with edge weight 1. And a BFS will traverse all the edges that is 1 away from the source node, and then it'll traverse all the edges that are all the nodes that are 2 away from the source node, etc., etc. And so it will correctly find the shortest path to a node. So this one is going to be always true. For the third one, the MST of a graph contains the largest edge in a graph. So if we create a graph where the largest edge is the only edge to a node, for example, if we had some graph over here, if we just had ABC, small example, and we had BC as the largest edge, in order to create a minimum spanning tree, we must include the edge BC. And so in this example, we show that the MST of a graph can contain the largest edge. How about we also draw a graph where the MST does not contain the largest edge? So we can have like a triangle, 1, 1, 10. And the MST in this example would be the AB edge and the BC edge. And that does not contain the largest edge of 10. And so the answer to this one is sometimes true. The fourth statement, given a valid topological sort, the last vertex has no outgoing edges. So this is kind of just in the definition of what a topological sort is. If we were to write out all the vertices, so if we had some topological sort and we drew all the edges in, all the edges should be pointing from left to right. And that means if you are the furthest right edge, furthest right vertex, on the topological sort, you cannot ever have any edges leaving that vertex. So we have that the last vertex has no outgoing edges, and that is always true because there are no more nodes to the right of that last node. The middle vertex in a topological sort of 3 or more vertices has no edge going into it. So if we were to create a topological sort, as I mentioned before, every single edge has to be pointing from left to right. However, we can just kind of draw an example where we have no edges in our graph, and our topological sort is just the 3 vertices with any single order. In that example, the middle vertex, so the B vertex, has no edge going into it, so that is true. However, we could also draw a graph, like the one I drew from before, where the B vertex has an edge going into it. So the answer to this one is going to be sometimes true. The next statement. Given a graph with all positive edges except one or more negative edges leaving the start node, Dijkstra's algorithm finds a correct shortest paths tree. We've mentioned in class that Dijkstra's is always guaranteed to work if every single edge is positive. However, we haven't really discussed in a lot of detail whether Dijkstra's works or not when you have negative edges. And typically we have said that it does not work with negative edges, except this is actually one example where it does work. So the reason Dijkstra's doesn't work with negative edges is because it assumes that it is always going to find the shortest path to a given node. So if you kind of, quote, hide a negative edge further along in the path, it won't know that that path is actually shorter if it's kind of blocked by a longer path. So you can see a short example of why negative edges doesn't work. So if we want the shortest path from A to C, if we had 100 here and like negative 1,000 here, we would never be able to detect that there's a shortest path from A to C because we never learn about the edge of a negative 1,000. However, if the negative edges only come from the source node, we will have information about every single negative edge that exists in our graph, and so we can run Dijkstra's like normal. And so actually, if the negative edges only are leaving the source node, Dijkstra's will always be true. Consider a variant of Dijkstra's algorithm, DAV1, that tries to find a target node and stops as soon as the target is in-queued. DAV1 finds a correct shortest path to the target on a graph with no negative edges. And so for the last statement, it is the dequeued. So that's the difference between these two problems, in-queued versus dequeued. We'll actually start with the last one because this is basically the definition of Dijkstra's. In Dijkstra's, if you're running it on a graph with all positive edge weights, as soon as a node is dequeued, you have found the shortest path to that node. And so this statement is always true. So conversely, if you only do it when you in-queue a node into the priority queue, what you're saying is that I have found a possible path to this target node, but I might have future updates that'll find me a shorter path. So the answer to this one is sometimes true, because it is possible by chance that the first path you found was the shortest path, but it is also possible that the first path you found is not the shortest path. Question 6, part B. For this problem, consider only graphs with non-negative edge weights. Naively, you'd assume that storing the shortest paths from a start vertex to every other vertex would require storing v-1 lists, one for each target vertex, requiring O of v squared space. However, we proved in lecture that the shortest paths actually form a tree, allowing us to store a single shortest path tree in O of v space. Suppose that we instead wanted to store the second shortest paths. So now, the clarification for this problem is that the second shortest paths is not simply another shortest path tree. It is the shortest path tree with the second, so it's the second shortest path for every single vertex. From a start vertex to every other vertex, for which a second shortest path exists, so a path that is the second shortest. Do the resulting edges form a tree? If yes, explain why. If not, give a counterexample. So the counter, for example, that we'll consider, and the answer here is no. The example that we'll consider is a triangle. So we have A, B, and C, and we can even give each one edge weight of 1 if we want. So the shortest path tree starting from A would be A to B, and then A to C. And this does, in fact, form a tree. Now let's say we want the second shortest path from A to B. So now since we can't take A to B because that is the shortest path, our second shortest path is A to C to B. And our second shortest path from A to C is A to B to C. Now if you take these two paths together, you do not get a tree. So the answer here is no.
So now we move on to 7a, where we were describing insertion sort in terms of travel functions, in which travel at I is basically taking the element at I and swapping it left as far as you can until it's in its correct spot, which is basically how insertion sort works. You start at the beginning and you swap left as far as you can, and then eventually you end up with a sorted list. Now the question is asking, if we do it in the reverse order, do we still end up in a sorted list? And the answer is no. This will not work. So here's the reasoning behind it. As you're doing insertion sort, basically what's happening is that, for example, let's say we're given this original input array. What's happening is that you're slowly creating a sorted portion and a unsorted portion. So what's basically happening is that with each iteration, you're taking this element and moving it left as far as you can until it is in its correct sorted position. And you keep repeating that process so that at the very end, you end with an entirely sorted list, right? The problem with the other direction is that you don't really have this like sorted portion that is growing. As a concrete example, let's consider this example. So this input. So if we were to start the sort at 2, the 2 looks left and sees that it is greater than the 1, and so the 2 does not need to move. Similarly, the 1 doesn't need to move as well, because when it looks left, it's going to see, oh, the 0 is less than, so I don't need to move. The 0 is going to swap with the 3 because it is lesser, and so we end up with this. And that's basically it. There's no more iterations that need to be done for this problem. And so, contrary to the first part, we don't really have a like sorted portion because these 1 and 2 are basically stuck where they are. So thus the answer is no, and as a simple counterexample, you can consider this input. All right, for 7b, we're going to consider a new MST algorithm called Pruskel's. For Pruskel's algorithm, we assume a connected, weighted, and undirected graph. And here's the following. The algorithm is the following. Basically, we initialize a set of edges, and for each vertex in the graph, just simply choose the cheapest edge that's connected to that vertex and add that edge to the set, and repeat until all the vertices are looked through. And now the question is, will this give you correct MSTs? And the answer is no. Oh, and also one important thing is that we assume edge weights are unique. So as a simple counterexample, let's look at this graph. We have A, B with a edge 1, B and C is connected with edge 4, and C and D is connected with edge weight 2. So now let's run through Pruskel's algorithm and see what gets outputted. So we initialize our set, and for vertex A, the cheapest edge leaving A is AB. So that's the edge, that's the edge that we add, AB. For B, the cheapest edge is also AB. And so ABs are in inner set, so we don't really need to do anything. CD is gonna happen similarly. The cheapest edge with C is going to be CD, and so that gets added to our set. And the cheapest edge for D is also CD, and so that gets added again. And so our resulting graph is a disconnected tree, or just not even a tree, it's just disconnected. And so as a result, this algorithm does not give valid minimum spanning trees because it's not spanning. It doesn't encompass the entire graph. Now we move on to 7c, where we are given an implementation or a class description of a min heap PQ. And the question is that for this data structure, it is able to handle mutations of the items that are present inside the priority queue. And we're trying to ask if it is fine to do something like this. And the answer is yes, it is fine to do something like this. So the key point was that we mentioned that we don't really care about runtime. And here's a key idea. The min heap, the PQ itself can't really detect whether something inside it has changed. So for example, if you just have a min heap PQ, something like this, and then one of these priorities gets updated, because you're just mutating the object itself and you're not doing any actual calls to the priority queue to change its priority, you can't exactly, the PQ can't really detect that. So the solution then is just, in order to ensure correct functionality for the min and remove min methods, we simply just reheapify the PQ but, with each call to min and remove min. So the answer is yes, reheapify every time. Reheapify for each call to min and remove min. So by doing so, yes, it's going to be slower, but we will ensure correct functionality because we make sure that the heap is a valid min heap before we do any additional operations on the heap. Now we move on to 8a. So for 8a, we are considering this new sorting algorithm called partition hybrid sort, which we are passing in an input, a low and high index, and a subsort. And partition hybrid sort works with the following. So it just does some index checking for step 1. For step 2, you do a single partition around input at index low, kind of similar to how you would do quicksort. And then you use subsort to sort the left and right subproblems. So now, given that, we want the worst case runtimes if our subsorts is different sorts. So if our subsort is insertion sort, if our subsort is merge sort, and so on. All right. So the basic idea of what's going to happen is that in the worst case, the partition is going to be very uneven. It'll basically partition the elements such that you can have, in the worst case, like 0 elements on one side and like n-1 elements on the other side. If you're considering like the middle being elements equal to the pivot and there's only one pivot, everything else is like greater than, for example. And so you can kind of just think of that as, in that worst case, how long do each of these sorts take on that many elements? So let's look at insertion sort. So insertion sort, if we have n-1 elements, we know that for an array of n elements, insertion sort will take theta of n squared. And so insertion sort is also, with this partition hybrid sort, is also going to be worst case theta of n squared. Merge sort. For merge sort, worst case is simply going to be n log n for an array of n elements. So n-1 elements doesn't change that at all. So it'll just be n log n. For LSD sort, we are specified that we are giving our answer only as a function of n. So we don't really need to factor in the constant of how many digits we're considering. And so we can simply just say that LSD sort is going to run in theta of n. And finally, for the fourth one, notice that the subsort we're using is actually just partition hybrid sort itself. But if you think about it, this is actually simply just quicksort, right? Because how quicksort works is that you partition it based on a pivot and then recursively call quicksort on the left and the right subarrays. And so we're doing exactly this here. And so if you remember then, quicksort is going to be worst case n squared in the case of really bad partitioning with very uneven left and right subarrays. All right, so now for 8b. For 8b, we're basically considering a combination of LSD sort with either merge sort and quicksort. So the basic idea is that typically for LSD, you just focus on a single digit, sort by that digit, and then keep applying it through all the digits until we end up with a sorted array. And the way to simply do digits is just by doing like a counting sort. Since your digits are only 0 through 9, we can just say, oh, there are these elements for 0, these elements for 1, and so on, and that does a sort for us. But now we're considering for each digit, we're going to use either merge sort and quicksort. And so in those cases, we want to figure out what's the worst case runtime. So if you remember for just LSD in general, the runtime is determined by the number of digits and how long it takes to process sorting each of those digits. So that's the idea we're going to have here. So for LSD merge sort, the worst case runtime is going to be W n log n. The reason why is because you have W digits, and for each digit, it will take n log n to sort that digit because you had to look at every element and look at every element's digit. All right? And the question now is this always going to work correctly? And the answer is yes. And the simple reason why is that merge sort is stable. So having stability is very important is because for LSD, as we are sorting from one digit to the next, we want to maintain the work that we've done from the previous sorting. So once we've sorted by some digits, we want to make sure that those are maintained as we continue on. We don't want to get those orders messed up as we're processing a later digit. So the key point is that merge sort is stable, and this is going to work. Now for LSD quicksort, the worst case runtime by the similar intuition is going to be Wn squared, because you have W digits, and for processing each digit, it requires at worst case n squared to sort that digit. So it's a total runtime of Wn squared. Does this always work correctly? No, it does not, because quicksort is, for most implementations, quicksort is actually going to be unstable. And we require the stability when combining with the LSD for it to work.
Okay, for number 9, we're taking a look at Dijkstra's algorithm, and we're seeing what happens if we change our normal binary heap-based priority queue to some other options for our priority queue. Right? Importantly, we're going to take a look at changes to the add, change priority, and remove min operations, and what kind of effect that has on the total runtime. First one, we're taking a look at trinary min heap PQ. This is the same as a normal PQ, a binary heap-based PQ, except instead of having up to 2 children, we're going to say we have up to 3 children. Asymptotically, this has no effect on the runtimes because it only makes a difference in the base of the log, but we know that it's just a constant factor away from log base 2, so the runtimes for all three of these operations is the same as our binary min heap PQ. Right, so for add, that is log of v. For change priority, it is log v, and for remove in, it is log v. Right. Same exact as our binary, normal binary heap-based PQ. It's v here, log of v, because there are at most v elements in our PQ. Since all these are the same as our normal binary heap-based PQ, our runtime for Dijkstra's overall is the same as before. So that's just e log v plus v log v. Right. So now we're going to take a look at the unordered array PQ. So this is now just a double array. The ith entry is holding the priority value of the ith vertex, and whenever we remove vertex, it will gain a null value, and whenever we add a new vertex, we will increase the size of the array by 1. This means we're kind of starting off with a size 0 array, and size 0 array, and we're continually increasing the size as necessary. All right. So our unordered array PQ, when we add to it, because we have to increase the size of the array by 1, in the case that we have to expand it. In the worst case, this is a linear time operation, so we can say it is v. Right, thinking back to resizing any array. For changing the priority, we can access the array directly and just modify the priority value. So this is a constant time. And then for remove min, we have to first find our minimum. So in order to find the minimum in our array, since it's unordered, we have to scan through the entire array. So this will also take linear time. Okay. So in total, our add is linear in v, change priority is constant, and then remove min is linear in v. So what effect does this have on Dijkstra's? So remember, for Dijkstra's, we are running v calls to add. So v calls to add. We're running O of e calls to change priority. And we're running O of v calls to remove min. Right. So for this one, what do we get? Well, we get v calls to add, so we get v times v plus E calls to change priority, so E times 1, plus up to V calls of remove min, so V times V. And that just gives us V squared plus E plus V squared. And that gives us a final runtime of V squared plus E. All right, so it's O of V squared plus E for our unordered array PQ. Finally, we have our ordered linked list priority queue. So this one is a linked list where it holds the vertex number and the priority value, and we make sure to maintain that our linked list is always sorted in increasing order of priority. So the very first link will be the smallest, right? In order to add someone to our priority queue, we will need to find its position. So given a specific priority, we have to move it into a specific position. And in order to do that, we have to traverse the linked list. In the worst case, we have to traverse through the entire linked list, and that gives us a linear time operation. For change priority, it's a very similar thing. When we're changing the priority, we need to find its new position. And that requires us to traverse the entire linked list, so that's also a linear operation. And then finally, for remove min, we can always just look at the very front. Since this is ordered, the smallest element will be the first link in our linked list, and that will be a constant time operation to remove it. So that'll be a constant time operation, right? Looking at Dijkstra's, we'll do the same analysis as we did for the unordered array PQ. We are making V calls to add, so V times V. We're making E calls to change priority, so E times V. And then we're making V calls to remove min, so V times. Okay, so what does it become? That becomes V squared plus EV plus V. So this will get dropped out, and we just get V squared plus EV. So final runtime, V squared plus EV. And that is number 9. Okay, number 10, our goal here is to find the exact value of compared to calls we make for each of these tasks. Right? In this case, we do not want to have our asymptotic runtime. We want to think about the exact value. So the very first one is our puppy cat dog scenario. Right? Recall that what this is how many compared tos we have to make between two boxes to be able to determine which one is the puppy, which one's the cat, which one's the dog. All right. Our best case is if we had these 3 boxes, E, C, and D. If we compare the puppy and the cat, and then we compare the puppy, or then we compare the cat and the dog, right? We'll see that the cat is greater than the puppy, and then we'll see the dog is greater than the cat. So we will have our ordering already, and we will know exactly which one is best. So we made 2 compared tos in order to get our ordering. In the worst case, we compare our puppy with our dog, and then we compare our cat with our dog, and initially all we get is that this box is greater than these 2. But we do not know the relative ordering of these 2 boxes. And we have to make one more comparison between the puppy and the cat in order to get our ordering. So this makes 3 comparisons for our worst case, so we get 3. Right. Next one, we are insertion sorting 5 numbers. Recall the best case for insertion sort is a sorted list. So if I just had 1, 2, 3, 4, 5. For every single element, starting from 2, there will be a single compared to call. 2 will look to its left compared to 1. It would say, I'm in the right position. It would stop there, move on to 3, look to the left, I'm in the right position, continue. So for all 4 of these elements, I make 1 compare to call. So in the very best case, I make 4 calls to compare to. The worst case for insertion sort is a reverse sorted list. So if I had 5, 4, 3, 2, 1. Right. Starting with number 4, I would make a single compare to, and I have to move it back. So this swap makes, in order to move this element backwards, I make 1 comparison. In order to move this has to go all the way back. Once 4 and 5 are swapped, this needs to go all the way back. So it needs to compare against every element behind it. So this will make 2 comparisons. This needs to make 3 comparisons, and this needs to make 4 comparisons in order for it to end in its correct location. So if you sum this up, we get a total of 10 comparisons for our worst case of insertion sorting 5 numbers. Okay. Next, we are inserting 5 numbers into an initially empty binary search tree. right? So let's take a look at the two cases. Best case for inserting to our binary search tree is if we have our bushy tree, right? So let's say I want to insert the numbers 1, 2, 3, 4, 5. The best way for me to insert them would be 3, 2, 4, 1, 5. This will guarantee kind of a balanced tree with 3 as the root. So if I inserted 3, now if I insert 2, I make one compare to call against 3, put it to the left. So one compare to call. Insert 4, make another compare to call. I insert 1, I compare against 3, I compare against 2, place it to the left. So 2 more compare to calls. And then insert 5, compare to 3, compare to 4, place it to the right. 2 more compare to calls. So this gives me a total of 6. So the best case of inserting 5 numbers is 6. And now the worst case is if I insert it in kind of linear order, so sorted order. So 1, 2, 3, 4, and 5. So I inserted 1. I compare 2 to 1, and it puts it here. That's one comparison. I compare 3 against 1 and 2, put it here. 2 comparisons. 4 is compare against 1, 2, and 3. 4, 3 comparisons, and 5 is compare against all 4 of these numbers. So 4 comparisons. Gives me a total of 10. So inserting 5 numbers into an initially empty binary search tree gives, worst case, 10 calls to compare to. Next is finding a successor from the root in a BST with 7 items. So the important thing to recognize here is that finding a successor does not need to make any calls to compare to. Right? In order to find our successor, we move to the right child of our root, and then we move to the left as much as we can. Right? None of these calls require any comparisons. We're just moving, kind of traversing our tree to the right and then to the left as far as we can until we hit null. In every situation for any binary search tree, this will not require any calls to compare to, so the answer for best and worst is 0.
For the second half of problem 10, the first statement is merging a sorted array of size 20 with a sorted array of size 30 to yield a sorted result. So if we have our 2 arrays, we have array 1, we have array 2, 1 and 2. Remember that when we're merging 2 arrays that are already sorted, all that we have to do is compare the first element of the 2. So in the best case, we're going to go through the entirety of the first array, and the moment you have gone through every single element in one array, you can simply append the other elements of the remaining array to the end in order to have a fully sorted array. So the number of compare to calls that we have is the number of elements that we have in our first array, which is 20. So in the best case, we have 20. In the worst case, we want to go through every single element. So we would go through all 20 elements of the first one. And for example, we would go through the 29 elements of the second one. The reason this is not 30 is because at the very end, when you have one element remaining, there's nothing left to compare it to. So technically, you're only making 49 compares to merge all 50 elements together. So we have the worst case as 49. Next, we have bottom-up heapification of an array of 7 items. So this is like when you run heap sort, you want to first take your array and just heapify it. So let's make an example array. In the best case, let's do 1, 2, 3, 4, 5, 6, 7. So this is our heap. In the best case, we already have our array as a heap already, so there's no movement needed. So the number of compare to calls that we have is we're going to compare 6 to 1, 6 to 2, 5 to 3, 5 to 4, 7 to 6, and 7 to 5. And so we have a total of 6 compares in the best case for a bottom-up heapification. So now let's try swapping out the 7 and the 6. And so here we're still trying to create a max heap out of this. And so the number of comparisons that we have is we're still going to compare the 7 and 1, the 7 and 2, the 5 and 3, and the 5 and 4. So far we have 4 comparisons for this bottom layer. Now we're going to compare the 6 to the 5, and we're going to see that the 6 is in the correct location. So that's another comparison. And then we're going to compare the 6 and the 7. And then we're going to notice that we actually want to swap the location of these 2 elements. So let's go ahead and swap them back. So we're going to put the 6 down here, the 7 up here. And now we need to once again kind of recursively call compare to on the 6 and the elements of the row below it. So we're going to now compare 6 and 1 and 6 and 2. And so we had that one compare for the 6 and 7, and now we have 2 more compares for the 6 and 2 and 6 and 1, which gives us a grand total of 8 total comparisons. So our answer is 8 in the worst case. For the next one, we have a binary searching of an ordered array of 7 numbers for a key. So let's go ahead and make an array of 7 values, 2, 3, 4, 5, 6, and 7. Now in binary search, we always start in the middle, and then we check if there's the right value. If it's not the right value, we want to go to the left if it's less than, and we want to go to the right if it's greater than. And so in the best case, we can say that we're looking for the number 4. And so after the first comparison, we are done. So in the best case, we're only going to need 1 compare to call. Now in the worst case, let's say we're looking for the number 5. When we go to 4, we notice that the number that we're looking for is greater than 4. So we're going to go to the halfway point of the upper half. When we get to 6, we're going to notice that, so we've done 1 compare to call so far. Now when we get to 6, we're going to do another compare to call, and we're going to see that, oh, our number is still too small. So now we're going to go to the halfway point of the lower portion. So between the halfway point of 4 and 6, so we have 5. And so we're going to do 1 more compare to call with that value to see that we have now found our target key. And so we have a total of 3 compare to calls. The final one is using counting sort to sort 52 cards by suit. So heart, diamond, spade, and club. And the key part of this problem is that we are using counting sort. And in counting sort, there are no compare to calls ever used. So in the best and worst case, we have 0.
Okay, for question number 11, I think the biggest challenge of this problem is understanding what is the procedure we're describing here, and how do we go about that. So just best way to talk about it is just, let's go through the first one as an example. So the very first, we have this set of values. We have a value for A, a value for B, and then we also just gave you what the best is, right? It might be a little hard to see, but we have a few of these values are bolded. So this one, and this one, and this 10 are bolded, right? And our procedure, as it says, is this: you must take the first sheep, and then you must walk forward between A and B spots inclusive. Once there are no sheep left, you're done. Otherwise, you take that sheep and you continue with this procedure over and over, right? So you see, for this listing of values, what we did is we took the first sheep, this one of value 1. We chose to move 2 steps forward, took that sheep, moved 2 steps forward, took that sheep, and then moved 2 steps forward to take that last sheep, right? And then this gave us a value of 13, which is the best we could do. The alternative from the first location is, oh, what if I moved 3 steps instead? I would have moved to this -1, right? From there, I could have moved to 0 or 10, but both of those options would have given me a worse value than 13. So we do not do that, right? So part A is just asking you to go through this process for a new kind of set of values and a new value for A and B, right? So you can kind of just walk through this example, just try out the different options yourself. So starting from 5, we have to pick this first one since it's the first sheep. Now we walk forward between A and B slots. So we're considering either -3 or 2, right? And then you have to consider that that's not the end of the problem. We need to get through the entire line. So from position 2, you might go to position 10. Otherwise, from -3, you can go to position 2, or you can go to position 10, right? So what are the options here? Well, if I went to 2 and then went to 10, that's a total of 12. If I went to -3, then 2, that's a total of -1. And if I went from -3 to 10, well, that's a total of 7, right? So of all these options, the best I could do in this back half of the array was go to 2 and then go to 10, which gave me this total of 12, right? That gets added together with the first sheep of 5, and my best path is to go from 5 to 3, from 5 to 2 to 10. And that gives me a total of 17 for best. Okay, for part B, we're now trying to fill in one solution for this problem. In this case, we're trying to do the naive recursive solution, right? So for our recursive solution, the first thing we want to do is fill in our base case, right? So what is our base case? Our base case is once we move beyond our list, right? That's when we know we're done. So if the value C is beyond the last index of our list, we know we're done. So our condition is just if C is greater than or equal to values dot length. In this scenario, there's kind of no sheep in the line. So what we can return is just return 0. So return 0. Okay. Because the value of a non-existent sheep, we can just say is 0. All right, on to the rest of the code. So we first need to initialize some value for best, and then we have this for loop, right? What ends up happening is our for loop will try and find the best we can do with our various values to move forward, but we have to find some value to start off with. And our choice will be values C. This ensures that what we're kind of keeping track of is always either the current sheep or something that is better than the current sheep, right? So this value S here for our for loop, what we're iterating over are the various step sizes we can take, right? So we want to be able to iterate over any of the values between A and B. So I want to initialize S to be A. And every single step, what I want to check is to make sure that S is less than or equal to B. I have not moved beyond B yet. So S is less than or equal to B. Okay. And I just increment S plus 1 every time. Okay. Now in the body of this for loop, what we want to see is what is the best I could do if I took value at position C and then the best I could do from position C plus S, right? From S steps forward in the line, what is the best I could do there? So my first line, which calls this max sheep naive helper, will assign it some value. So int val equals, and I want to add value C to this. So values C plus max sheep naive helper. What I want to pass in is I want to pass in the same values. I want to pass in the same A and B. But then the position I want to pass in now is the position S steps forward. So I want to pass in C plus S. Right. Given this val, I want to determine whether or not selecting the sheep S steps forward is better than what I have right now. So I will just reassign best to be the better of the two. Right? We can do this using math.max. So I can say best equals math.max of val and best. Right. So if val ends up being a value that is better than what I have right now, I will reassign best. Otherwise, best will still be the same. Right. Once I'm done with this for loop, I will have checked every step forward from where I currently am, and best will be the best value it can be. And then it returns best at the very end. Okay. So that is the end of the code for part B. Okay, part C. So this is a really challenging part of the problem. In this part, we're not asking you to come up with something better than our naive recursive solution. We want to use dynamic programming to make our solution a little more optimal. If you just look back at the naive recursive solution, these calls to max sheep naive helper, it becomes inefficient. We actually get this exponential runtime, or definitely much more than linear, because we're constantly looking forward. We have to recalculate the best value at a specific position many, many times. Right? So let's try and do it better using kind of a dynamic programming approach. For this problem, we said that the description of Qn and the DAG are optional, but I'll fill it in just to kind of give you a better idea of how we approach these dynamic programming problems. So Qn, what it will represent for us is kind of the best you can do if you started at position n, right? So this is the best value if started at position n. Right? That's what Q1 represents. So with this kind of subproblem, well, we know that Q0 from our first position, that will be our final answer. And that's what eventually will lead to a very quick runtime, is that we can build up to this Q0 very quickly, and we can immediately just return it, because it'll represent what the best value is if I started at that position. Right? Now in terms of the DAG, so if I drew every position, so I'll use these values here. So 2, 1, -3, 6, 8, -2, -1, and 4. Right. I want to make my DAG so that an edge from I to j indicates that subproblem I is useful for subproblem j. Right. So what is useful for our first subproblem? Well, the things I actually want to know are what is the best value from 2 and 3 positions forward. Right. So what is the best I could have done from these positions forward? So in reality, the DAG is actually kind of pointing in the opposite of our normal way, and -3 would point to 2, and so would 6. Right. And this kind of continues on. Well, what was useful for solving problem number 1? Well, 2 and 3 steps forward, those are the ones that would be useful. So 6 would be useful for solving 1, and so would 8. Right. And this just continues. So 8 would be useful for 3, -2 would be useful for 3. For 6, we would want -2 and -1. For 8 would be -1 and 4. For -2, it would just be 4. And then for -1 and 4, nothing is useful for solving them because we already know, right? At this point, what we've kind of built up is the idea that the things at the very left, they require things to the right of them, right? -1, -4 are the only ones that don't require anything. And that leads us to kind of our solution, which is that this dynamic programming problem is best solved by filling in this table from the right, from a larger value of n, because they are not dependent on as much, right? What is the best value if I started at this position? Well, the best value is exactly 4, right? Is if I just started here, there's nothing else I can pick. There's nothing else left in my line of sheep. I chose 4. Same with -1. Since A and B are 2 and then 3, from -1, I would pick this sheep, and then I would have to move off to the end, off of my list. So that I would be done, right? At -2, what is the best I can do? Well, I can only pick 4, and that does improve my value, so that is better. So that gives me a value of 2, right? Because -2 plus the best value of 4. From 8, well, what is the best I can do? Well, I can either go to -1 or I can go to this 4 position, right? Better one is 4, so Q of n at this position is 12. 6 looks at these 2 positions, looks between 2 and -1. The better one is 2, so it picks that, makes a value of 8. -3 is looking at 8 and -2, so looking at these Qn values of 12 and 2, it adds itself to the better of the 2, so it adds -3 to 12. That gives you a value of 9. Some students noted that 1 was not reachable, so we allowed any value here. But the intention is that the algorithm itself will not know that. So from position 1, it would still take a look at 2 and 3 steps forward. So it'll take a look between 8 and 12. It would see 12. It would choose that one, and it would have a value of 13. And then from the very first position, we're taking a look at 9 and 8. It says 9 is better, so it chooses 9, and it fills that in with a value of 11, which is our final answer for best. Right, that's correct. I'll say for this problem, the most common incorrect solution would be taking every single location and just using the naive recursive solution, calculating what would the best value be if you ended at a certain position. In this example specifically, we selected 2, then -3, and then 8, and then 4. And it just so happened to be that we ended at the last element in the list. But this is not always true, which is why this approach was not entirely correct. It's also a different runtime, and it does not relate the subproblems to each other. Right? It does, in this situation, it does give you a value of 11 in this last spot, so it becomes very easy to see that it makes it easy to think that that is sufficient and will always work. But in many other examples for various values and A and B, this solution will always work, whereas the other one will not always give you a convenient location to find your solution. Right? Okay, so very last thing is we want to talk about the runtime of what this dynamic programming solution would be. Well, what our procedure was for every single position of n, we just looked at Q of n for between A and B steps forward, right? So like at position 8, we looked between 2 and 3 steps forward, so we looked at these two positions. And for every single position, we would do this, right? So our runtime essentially becomes, for every position n, we do something, and this something is search for all the positions between B and A steps forward, right? So our runtime becomes n times B minus A, since that is the range we are searching for every single slot, and this becomes a theta notation. Right. There's really not much left to the algorithm. There's a few extra constants and arithmetic plus or minuses, but the range we're searching for every single position is size B minus A. And since we do this for every single position, we get n times B minus A, and that's our final runtime.
All right, so now we are moving on to 12, the sibling tree problem. We're asked to implement different parts of the sibling tree implementation. So the first part, we're asked to calculate the largest sibling. We're given a sibling tree, we want to calculate what is the largest sibling value. Either it's going to be ourselves or it's going to be one of our siblings. So looking at this initial implementation, we have a line given to us where if t equals null, we return 0. The first thing that stands out to me when I see a line like that is that this is going to be a recursive implementation. And so let's try to frame this in a recursive framework. So if the largest sibling method returns the largest value, and remember that siblings only go in one direction, it only goes to the right. So let's try to think of it this way. Let's say we calculate the largest sibling value for everyone to the right of us. Then the largest value overall is either going to be anyone to the right of us or just ourselves, basically, especially if we're the child. So if you're calculating the largest sibling from the child, then it's the largest value is going to be the max of ourself and anyone to the right of us, right? If there's no person to the right of us or no tree element, then it's just going to be 0. That's basically our base case, right? And so from this recursive framework, we can fill in the implementation, which is simply a single line. We're just going to return math.max of our own value, which is t.item, or the largest sibling value of our sibling. And that's it. So now we move on to 12b, in which we are asked to implement a post order traversal of the sibling tree. So if you remember what post order is, one thing that's good for this problem is just think of how you would do this post order, assuming it wasn't a sibling tree, it was just a normal binary tree or just a normal tree, and then kind of extrapolate from there. So if you remember for post order, how post order works is that you must visit all of your children first and then visit yourself, right? So post order is visit everyone below you, then visit yourself. All right, so if we look at this tree as an example, so for this 4, if we were to call post order on this 4, we must make sure to visit 7 and 6 before we visit 4, right? So, and post order, and especially for this, is going to be important that post order is going to be done recursively. And it's also kind of hinted by this edge case. So in this base case, if t equals null, then there's nothing to really visit. So we just return since there's nothing to really do here. All right. So now, if we want to visit our children first, that's equivalent to calling post order on our child. And that's exactly what we're going to do. So we're going to call post order on t.child and pass in our visitor. And here's where the subtlety comes in. So if we look at this far as an example, so assuming t is 4, we're calling post order on t.child, which is 7, but we also need to make sure that we visit 6 as well before we visit ourselves. But visiting 6 comes from visiting 7, actually, right? Because there's actually no direct connection between 4 and 6. It's coming through our child. So when we're in the recursion with respect to the child, we need to make sure that we visit the siblings of 7 before we visit 4. So how we're going to do that is we're going to have this call here, post order t.sibling with the visitor pattern again. All right. And in the middle is where we're going to have our visit, our calling v, our visitor. Our visitor has a visit method, v.visit on the tree t. So the reason why it's in the middle is because by calling post order on t.child here, so if we do it, let's say we're calling it with respect to t equals 4, all right? So this is t right now, it's going to be with respect to 4. So when we call post order on t.child v, it's going to visit the 7, and as a result of the later recursive call, we're going to also visit the sibling of 7, which is 6. And then once 7 is finished visiting his siblings, which is 6, then do we actually return from t.child and visit t itself. So now we finally move on to 12C, in which we are given a sibling tree and we want to calculate the max path of this tree, which is the path with the maximum total weight. So the key idea is that we're going to be using post order and to basically build these max paths from the bottom up. Because notice that we initialize our max pathfinder is a visitor. So it's a visitor v, and so we implement the visit function. We call post order on the sibling tree, and then we print out whatever result it is. One thing we also know is that our visitor may be destructive, and that's going to be important for our solution actually. So before we move on to the actual problem, let's consider a small example of this tree. So let's consider just the one part of this tree, which is just 2, 2, and 4. All right. So if we consider just 2, we're considering this point. Well, one thing, by doing post order, we're basically building from the bottom up maximum paths. So I guess the 2 by itself doesn't really have anywhere to go. The maximum path using assuming a tree of just 2 is simply going to be 2. The maximum path using just 4 is simply going to be 4. Now if we were to consider the 2, now notice that there's basically 2 options. We either are going to use this 2 here and make it as basically the connector connecting 2 of its children as one long path, okay? So in this case, the max path is going to be 8, right? But by making this choice, this is basically going to be where our path turns, and there's no way we won't be able to use anything above this 2 if it were to exist, all right? The other choice is basically use this 2 as a connecting path that's continuing along upwards that we're not aware of. And so in that case, what I mean by that is that this would have a path of 6. So another max path would be 6, in which case we're just using this as a connection for a longer path up ahead. But we don't know which one is going to be better, right? But what we do know is that at this point, at this node, if we were to use this value, then the max path is going to be 6 for anything below it as well, especially because all of these values are non-negative, right? And so we're basically considering, at each juncture, we're considering 2 choices. Either we use the node that we're considering when we're visiting, either we use a node we're considering as basically our connector with 2 paths, and our path stops there, or we use this node as a connection to a longer path up ahead. So that's basically what we're going to be implementing here, right? So the variable we're going to be keeping track of is just whatever the best path is that we found, right? So this is going to be basically global, and we're just going to update as we find a best path. So initially, we'll just say the best path is 0. And our result is just returning this value. Best path sum. Okay, now let's get to the visit. So given this information of like these two choices, we're going to basically implement that. So how we're going to do that is, well, if we have a bunch of children, so like let's look at this case here. Let's say we have a tree of just 4 with 3 children. Since all of these are non-negative, we know that the best path, if we were to use this 4 as a connector, is just take the 2 largest children, right? And that's exactly what we're going to do. That's why we had those largest and second largest methods implemented previously. We're going to use those now. So we're going to save those as instance variables, or sorry, as local variables. We have our int largest equals t dot largest sibling with t dot child, int second largest equals t dot second largest, which was also an available method from the previous page. All right. So the best path using, so we're going to say int best path as root, or basically using this item as basically the turning corner for this path. This value is going to be equal to largest plus second largest plus our own value, which is t dot item. All right. Now we're going to consider the other option, in which we're just using ourselves as a connecting path for a longer path up ahead. And that would be, I'll call it subtree total. Subtree total. And that's going to be equal to just using only the largest. Largest plus t dot item. Right? So one important thing we need to do is that once we finish calculating both of these, we need to set our own t dot item as the subtree total. Because basically what that's doing is that's going to communicate up ahead for higher up in the tree what the value of the path is if you were to use me as part of the path, basically. And so it's very important that we set t.item equal to subtree total. The last thing we need to do is just actually calculate what our best path is. And so to do that, we just set best path sum equal to math.max of either using myself as the root of the path, or what we currently have. So that would be either using what we currently have, which is best path sum, or the best path as root. So what this will effectively do is that for all, because we're going to eventually visit every node, we're eventually going to visit, okay, if we use this as the root, what is our best path? What is our best value? If we use this as the root, what is our best value? And we're going to check that for basically all of our values. And so this will be the implementation of visit, and that is it for 12C.
Problem number 13, flights planning. So this is a very challenging algorithm design problem on a graph. Consider the snrplt, SNRPLTE, shortest no repeats path less than exists method below. It returns true if there exists a path in the graph from S to T, so S and T are two vertices, that 1 has total weight less than or equal to W, and 2 has no repeated vertices, i.e. each vertex appears at most once. So the inputs into snrplt are the graph G, a vertex S, a vertex T, and a weight W. So for example, on this graph, if we start at the node 0 and we have our target as the node 2, as long as we supply a value of W that is greater than 0, and we see that there exists a path here which has a total weight of 0, then snurple T will return true. Snurple T does handle both undirected and directed edges. Now for the runtime, we're going to say that the runtime of snurple T is theta of f v comma e, where f v comma e is some unknown function that is bounded by big omega v plus e. So we don't really know what the runtime of snurple T is, but we can kind of abstract it away and say it is just f v comma e. So the problem is, given an undirected, unweighted graph G, where each node is an airport, and each edge indicates that there exists a flight between the two airports. Suppose we want to know if there exists a path that visits every airport exactly once, which we'll call a world tour. In other words, you want to write the method below. So we want to write the method WTE and give a concise but thorough explanation of how you would solve WTE for a given graph. It must have runtime theta of f v comma e, i.e. the same as snurple T. So we want to make an algorithm that visits every airport exactly once. And so in a graph, kind of thinking back to the different concepts that we have, it sounds like an MST. And so the key part of that is we want to find a tree, which means the number of vertices is going to be, the number of edges in this path is going to be v minus 1. This is the only way to reach every single vertex exactly once. However, because snurple T solves for a path and returns true if it has a value less than W, we can't really count up and just make every edge weight 1 and pass in v minus 1, because technically a path of edge weight of total weight 1 is less than v minus 1, so it will just return true. So to solve this, our first kind of key breakthrough is that we're going to invert every single value. So step 1 is we're going to make a graph. So we're going to make a new graph. We'll call it H, and we're going to set all edge weights to -1. All edges weights to -1. And the W that we're going to pass in eventually is now just going to be the negative of v minus 1. So essentially we want to make a counter until we pass some threshold, but we can't do that with using positive values because the threshold is something less than some other value. So instead we got to count in the negative direction. So now if we were able to grab v minus 1 edges, their total weight would be negative v minus 1, and now snurple T will return true if this tour exists, if the world tour exists. The next problem, however, is that we don't know what the starting airport is, and we don't know what the target airport is. In the problem, we can pick any single airport as a start, or the target. So one naive way to do this is simply to run snurple T from every single start airport to every single target airport and do every single possible combination. However, if we look at the runtime, we see that our runtime requirement is theta of f v comma e, which means we can only run snurple T a constant number of times. Running it from every different combination of source and target is not a constant number of operations. So we have to come up with some other way in order to find if a tour exists or not. So what we're going to do is we want a way to have all the starting node, every single node be considered as a start, and all the nodes be considered as an end at the same time. So we're going to create something I call a virtual node or a fake node. So fake node. So we're going to make two fake nodes. We're going to make a start fake node and an end fake node. And for both of these, we are going to connect each node to every single other node. Connect to all nodes with edge weight of 0. So we don't want to count this as part of our number of edges that we need because we still need v minus 1 real edges. However, this will just be a starting point. So now we can start from any single node, and it'll just cost 0 to get from the start node, our fake node, to one of the real nodes. And at the very end, we can exit the graph by going from any of the nodes to the end node with weight 0. And so finally, now all we have to do is run snurple T, S-N-R-P-L-T-E, and the parameters we want to pass in is we want to pass in our new graph that we created. We want to pass in our start fake node as the starting node. We want to pass in the end fake node as the end node. And we want to pass in negative v minus 1, which is the number of edges that we want in our total graph. And so this is one call to snrplt. So our runtime will still be theta of f v comma e. And if this snrplt function returns true, that means there exists a world tour that visits every single airport. And if it returns false, it means there does not exist a world tour.
As an additional note to this problem, I want to talk about one of the more common mistakes for people who are very, very close to the correct solution, but were just slightly off and did not receive full credit. So the thing that we saw most often were students who did not create our two virtual nodes, our start and our end nodes, and connect it to all the vertices in our graph, and instead try to find two vertices that were already in the graph to serve as our start and end. So some common procedures they used were trying to find two vertices with degree 1, choosing any vertex and any adjacent vertex, or just choosing vertices arbitrarily, or maybe using some BFS or DFS or some form like that. So I will provide two counterexamples, which will show why this approach of trying to find a vertex, two vertices in the graph is insufficient. So the first one is, let's draw a graph, which is just a straight line. So let's say A, B, C, D, E, right? So for this graph, the selection of a vertex and its adjacent, or the selection of arbitrary vertices will not work. And the reason it won't work is, let's say I chose arbitrarily the vertex B as my start. And now if I chose C, because it's adjacent to it as my target, I find that there is no world tour from B to C because there's only a single edge and I can move nowhere else, right? Since you cannot backtrack on this edge, you cannot revisit any vertices, I can't get back to any of these other vertices once I've moved to C. So if I ran snrplt on B and C as my start and end, even if I pass in the correct value for W, I will not return true, even though in this case there does exist a world tour. If I started at A and I ended at E, so this is my real start, and this is my real end, then I would have been able to find a world tour. For cases like this, I think some students were considering degree. So those who chose to choose their start and end based on their degree would have been correct in this example. They would have chosen the two vertices with degree 1, A and E, and they would have returned true in this scenario. The other example that shows why just choosing degree 1 doesn't work is if I just drew a circle. So B, C, D, and E, right? Or any other graph of the cycle. In this example, there is no vertex with degree 1. We can see that there does exist a world tour. If I choose any two neighboring vertices as my start and my end, I can find a world tour because I can just go around in the circle. But since there is nothing with degree 1, most of these solutions just said, in the case there does not exist something with degree 1, just choose arbitrarily. Right? And this is insufficient because if I chose arbitrarily in this case, I might have selected, let's say this B as my start, and then this D as my target. And I would said there is no world tour because I can move from B to D or vice versa, but I cannot pass through and visit everything. I cannot visit anything else in the circle and get back to the target afterwards, right? So if I chose these two vertices as my start and my end, I would have returned false when the actual answer would have been true. So these two counterexamples were the reason why we were not able to award full credit for a lot of the solutions which correctly negated the edge weights, but did not create two virtual nodes and instead just attempted to find candidates for start and end inside of the existing graph.